Welcome, seventh graders. Today we are looking at Digits topic 2.1. And so our objective for today is to recognize a proportional relationship in a table. So as you work today, we're going to be looking at proportional relationships and examining them within a table. So this is going to build on what we worked on last topic. So you can take this topic and turn it into your learner's question for the day. A proportional relationship is able to be shown as an equivalent ratio. So what's great about this is that this is a skill that we already worked on last topic. We spent a lot of time on that. So we're familiar with equivalent ratios, and we can always make equivalent ratios by multiplying or dividing. So we will come back to the equation piece, but for now I want to look at this example. So we have a diagram that shows a series of squares, and the side length and the perimeter of each square are labeled. So our first square, we have a side length of 1, which gives us a perimeter of 1, 2, 3, 4. Remember, perimeter is the rim around the outside of a shape. So if each side is 1 unit, 4 sides makes a perimeter of 4. So we can see that listed in the table. If the side length is 1, the perimeter is 4. Then we're going to write the ratio of the perimeter to the side length. So my perimeter is 4, that's my numerator. My side length is 1, that's my denominator. Let's check out our second square. This time we have a side length of 2. 2 units on every side, so the perimeter would be 2, 4, 6, 8. So as my side length is 2, my perimeter is 8. If I write that as a ratio of perimeter to side length, it's 8 to 2, which notice we can reduce to 4 over 1, which gets us back to our initial ratio. So let's check out a square with a side length of 3. 3, 6, 9, 12. I get a perimeter of 12 because I have 4 sides that are each 3 units. 3 times 4 is 12. So when my side length is 3, my perimeter is 12. And my ratio of perimeter to side length is 12 to 3, which reduces to 4 over 1. Okay, using the pattern in the table, we could guess what would come next. We've looked at side lengths 1, 2, and 3, and then we're going to jump to 4. So we could fill in a 4 here, but let's make sure that a side length of 4 would correspond to a perimeter of 16. If I have 4 sides that are each 4 units long, 4 times 4 is 16, so that checks out for my perimeter. If I'm going to write this as a ratio, 16 to 4, which also reduces to 4 over 1. So let's increase the size of our square so that its side length is 5. To find my perimeter, I need to take the 4 sides times their length. So 4 times 5 is 20. And if I'm going to write it as a ratio, that will be 20 to 5, which again will reduce down to 4 over 1. My final perimeter is 24, so I'm looking for a square with a perimeter of 24. If I know there are 4 sides, 24 divided by 4 is 6, so my side length must be 6. As I write this as a ratio of perimeter to side length, I can put 24 to 6. If I reduce that to lowest terms, 24 and 6 both have a common factor of 6. 24 divided by 6 is 4. 6 divided by 6 is 1. So again, my ratio will reduce to 4 over 1. So the question we should ask ourselves is the relationship between the perimeter and the side length of a square proportional? So looking in this table, I notice that every proportion reduces to 4 over 1. So that tells me that the relationship between perimeter and side length is proportional. And I know because each ratio reduces to 4/1. So as long as I have the same ratio when I reduce, then I know that it's a proportional relationship. So let's look at another example here. The diagram shows a series of squares drawn on graph paper, but this time the side length and area are labeled. Now remember, with area, our formula for area says the area equals the length times the width. So I'm going to look at the length of the square times the width of the square. However, since it's a square, my length and width will be the same. So I can take that side length and I can multiply it by itself, or I can square it. So as I'm filling in my table here, let's look at our square whose side length is 1. If I take the length, which is 1, and the width, which is 1, that gives me an area of 1. So in my table, I'm going to write the ratio of the area to the side length. My area is 1 and my side length is 1. So I have a 1-to-1 ratio. Let's check out our square whose side length is 2 units. So to find the area, I'm going to take the length, which is 2, times the width, which is 2, and 2 times 2 is 4. So when my side length is 2, my area is 4. So if I write the ratio of the area to the side length, that becomes 4/2, which reduces to 2/1. Right off the bat, I'm noticing a 1-to-1 ratio and a 2-to-1 ratio, and that's grabbing my attention because that seems different. Let's check out a square with a side length of 3. To find my area, I'm going to take length times width, or side times side, which is 3 times 3, so I get an area of 9. On a side length of 3, I get an area of 9. So as I'm writing the ratio of area, which is 9, to side length, which is 3, I can reduce this. 9 and 3 both have a common factor of 3. 9 divided by 3 is 3. 3 divided by 3 is 1. So this reduces to 3/1. So now I have 3 different ratios: 1-to-1, 2-to-1, 3-to-1. Let's check out our next side length. If I have a square whose area is 4, that means I have a side length of 4, because 4 times 4 is 16. So if I write this as a ratio of area to side length, that's 16/4. And I can reduce this to lowest terms by dividing my numerator and denominator by the greatest common factor. So 4 would be my greatest common factor. 16 divided by 4 is 4. 4 divided by 4 is 1. Again, I have another new ratio: 1-to-1, 2-to-1, 3-to-1, 4-to-1. As I look at a side length of 5, if my side length is 5, my area is side times side, or 5 times 5. That gives me an area of 25. So if I write the area to the side length, 25/5 is my ratio, and I can reduce that to lowest terms. I'm going to write below to make a little more room. 25 and 5 both have a common factor of 5. So if I divide 25 by 5, I get 5. 5 divided by 5 is 1. So I get a reduced ratio of 5-to-1. And finally, if I have an area of 6, that means that side length times side length equals 36. Well, I know that 6 times 6 is 36. So if I write this as a ratio of 36/6, I now have a ratio I can reduce, because 36 and 6 both have a common factor of 6. 36 divided by 6 is 6. 6 divided by 6 is 1. So this time, if we're asking if the relationship between side length and area of a square is proportional, I would say No, because we don't have a common ratio. We have a different ratio each time. So that's how we'll use tables to help us examine ratios. We can organize our information so we can easily compare it into a table. And we're always looking for a common ratio throughout our table. Let's look at a few more examples. You might be given some tables like this and asked to determine whether it shows a proportional relationship between x and y. So we can always take our y value and put it over our x value to set up a proportion and make sure that it's the same in every row. So here I'm going to take my xy table and I'm going to write it as y over x and reduce. So my y value is 4 and I'm going to put 4 over 8. 4 over 8 can be reduced because 4 is a common factor of 4 and 8. So if I divide 4 by 4, I get 1. 8 divided by 4 is 2. In my next row, I'm going to put y over x. So I'm going to put 3 over 6 and reduce to lowest terms. 3 and 6 have a common factor of 3. 3 divided by 3 is 1. 6 divided by 3 is 2. So far, I have a common ratio. So far, my table is proportional. Now I'm going to take y, which is 1/4. I'm going to work over here so we have a little more room, over x, which is 1/2. And I need to reduce to lowest terms. This is tricky because I have a fraction in a fraction. So remember, to simplify this, we can always multiply by the reciprocal of our denominator, and that will help us eliminate fractions within fractions. So I'm going to multiply by the reciprocal, which is 2 over 1. Whatever I do on the bottom, I have to also do on the top. So now this becomes 1/4 times 2 over 1. If I multiply straight across the top, 1 times 2 is 2, and straight across the bottom, 4 times 1 is 4. That becomes 2/4. And in my denominator, 1/2 times 2 over 1, that will cross cancel 1. So now I have the fraction of 2/4, which can be reduced to 1/2. So my common ratio remains. As we look at our bottom column, as long as we get a ratio of 1 to 2, then our table is proportional. So this time we have a mixed number, which is not helpful. So let's change this to a improper fraction. So we have 5 and 1/2. I'm going to start with my denominator and multiply by the whole number. 2 times 5 is 10, plus 1 is 11, and I keep my denominator. So I'm going to rewrite this as 11/2. Now I can write my proportion, but I'm going to take a little more room since I have a fraction again. So I have 11/2 to 11, my y over my x. And I want to reduce this to lowest terms. So I want to get rid of my denominator here. Whenever I want to get rid of my denominator, I can multiply by the reciprocal. The reciprocal of 11 would be 1 over 11. Whatever I do to the bottom, I have to also do to the top. So now this cancels in the bottom, and in the numerator, I have 11/2 times 1/11. Well, my 11s here will cross cancel, so I am left with 1/2. Since I have a common ratio in every row of my table, I would say that this is proportional. Let's check out our second table here. We will pick this one up in the next video.